It's almost the time to start, so I will start this session. This session is an IoT working group, and my name is Yasunori Owada, the chair of this IoT working group. So today we have two sessions from 9 and from 11. So this IoT working group is sharing the experience and discussion and collaborations on the IoT platform infrastructure and services. So if you have some experimental results and the testing, and also you have the platforms for the IoT, please share such experience to this IoT working groups. Yeah, and today, this is a chair and co-chair and advisor of this IoT working groups. The chair is me, and the co-chair, there are three co-chairs, the Bushan and Sampol and Sengjong Seok. So, and one advisor for the NICT also, Kawai, Eiji Kawai-san is the advisor. And this is the agenda of this first sessions. And the firstly, I will talk about the update of the resilient regional information sharing platform called NAVNet. Previously, I had talked about this related technologies on the APAN58 or something. And today I will update the technology part and share some technical stuff. And the second one is Himanius Pandi from ICT4D. And he will introduce some South Asia IoT land space with focus on Nepal and emerging LDCs. So, and the last presenter of this session is Kafre-san from NICT, and he will introduce some directory service for IoT device profile and application data management. And the second session start from the 11, and we also have three presenters. So one is Pietro Semi. I'm sorry, I cannot pronounce the name of him. Pietro Semoli Emano. ICTP, and he will present IoT communication technologies. And the second one is Sebastian Bucci, IT University of Copenhagen. And unfortunately, he has not come here, so, and he will present perspective in small satellite IoT networks. And the last presenter is Navid Arshad Lahore University of Management Sciences. He will present sustainable air quality monitoring with low-cost mobile sensors. So let's move to the first presentation of this session. Sorry. So firstly, I will introduce some technology update of the NAVNet. The title is Resilient Information Sharing Platform with Distributed Edge Computing. The background of this technology is started from the March 11th to 2011. So we have a great East Japan earthquake in Japan, and we faces some big trouble for the communication at that time. So many mobile base station stops, and also the even the affected area, they cannot communicate anymore, but the non-affected area also, they cannot hardly to communicate using the mobile phone because of the phone network is congested, so the operator restricts the call acceptance ratio up to 90%. So it's a little bit hard to communicate after the earthquake happens, and also tsunami destroyed the infrastructures. So to avoid such kind of communication blackout after the earthquake, so we need some additional communication systems to provide the immediate communications within the disaster-affected areas. So we developed some technologies called NavNet. So this is a short video for introducing the NavNet systems.
When a natural disaster occurs, securing information distribution network is the most critical factor to overcome it. However, mobile phone, PC, and TV that we use every day won't work when the servers or base stations are disabled by physical damage, blackout, or congestion. National Institute of Communication and Technology developed a disaster-resilient network system called NavNet. As the name indicates, the network is spread in a mesh shape like human's nerve system. NavNet can be in operation by just installing dedicated base stations in the area without any complicated settings. If some of the servers or base stations are disabled by a disaster, others can cover for them by bypassing the damaged route and keep communicating. There are two types of base stations, stationary and portable. You can expand or change coverage area by combining those two types of stations. NavNet can be used not only in a disaster, but also in the usual times. For example, it can be used for bus location system, location-aware shopping support system, or closed-loop high-security information sharing system. You can deliver a variety of contents and services by connecting various devices to NavNet. NavNet can serve as a resilient information infrastructure for local areas in both emergency and usual times.
Yes, this is an overview of the NavNet systems. And last August, the current Prime Minister in Nepal has come to NICT to observe the research activities, and he also we presented the NavNet systems to him directly. So, and this is the architecture difference of the NavNet system and our current access network infrastructures. Maybe, or you know that the internet is a mesh topological networks to, so it's have some resilience to the failures and the leak disconnection. So it automatically reload and keep the communications. but the access side is like a three topological networks. It's split it to the, for example, the mobile networks, access networks, the link split it to the each base stations, and they provide the wireless access services. So if some links are disconnected, the leaf side, bottom side, is getting out of service. So we are now, the NavNet is trying to create mesh topological access networks. This is the one thing. So, and the other things is distributed server and database functions inside the access network nodes and distributedly operated that such services. So current mobile application and any application services some servers are located in some clouds or on the internet side. So if the internet access is not available, any application cannot be used. But the NavNet provides the minimum services, so like mobile communications and also the message advertisements. Such kind of minimum services can be operated on the base stations, and they are distributedly operated. So if the internet connection is not available, such the minimum application service can be continued only in the local networks. So this is the functionalities of the NavNet provided. So it supports a mesh topological network, so it can support the automatic path switching mechanisms, and also they make a phone call. So the NavNet itself have SIP, like a SIP server functions on each base stations, and there are no centralized servers. So it's distributedly operated. So if the phone application registered to the nearest base stations, its phone number is registered to the nearest base stations. The phone number and also the location shared among the base stations, so it can keep communication without using centralized SIP servers. And also the other stuff is base networking functions. So it supports the VPN or multi-homing and the message advertisements and the local application services. So this is a little bit different of the conventional networking systems, network hardware or functions. So it have the the NavNet is combined with the networking function and also the application service functions, both together, and it creates some service, networking services. So it provides some cloud services on the base stations, and they provide, they can cooperate with the other base stations. One example of the message advertisement, this application demonstration I will present it later. And if they send a voice message, we use some distributed database systems applications. If some data is inserted to the database itself distributedly operated and synchronized automatically. So the inserted data is shared and synchronized immediately in the base stations. So using such functions, we can implement some applications, local applications, without using any cloud system and server, centralized servers. So after this one, I will show you how the NavNet mesh topological and the path switching mechanisms are operated. So if there is a 4 NavNet base stations, and they are connected through like this kind of mesh topologies. And then each base station detected each other and select them, automatically selected the master node. And the master node calculate the VLAN path over the this kind of physical mesh network topologies, and set up the different shape of the tree paths and assign the VLAN ID to each path. For example, the VLAN ID 101 is like this shape, and 102 is blue dotted line. 103 is green, and 104 is this kind of. So several the candidate VLAN path is automatically calculated and configured to among the base stations, and if the base station 2 and 3 want to communicate each other, the minimum cost path, for example, this example 104 is the minimum path. Is selected. The VLAN 104 is selected to communicate base station 2 and 3. But if these links are disconnected, the disconnected information is shared to the base station, and each base station automatically select another candidate path to reach to the destination base stations. So the base station 3 automatically change to the VLAN 101 and keep communications. So this kind of switching technology, and also we provide some application service technologies, combining with the provided as a Docker image. So if you want to install this NavNet functionalities into your hardwares, you just run the Docker and get the image for this NavNet image. Then the hardware can work as a NavNet base stations. So we provide the NavNet functions as a Docker image. And if the NavNet Docker image is operated on the hardware, the NavNet itself have such as kind of switching functionalities. So they create the namespace isolated to the host side, but internal container internal network devices should be connected to the outside of the real hardware NIC or network devices to operate such kind of interaction from the container inside to the host side. So we implement some techniques to control the host side networking bridging functions from the inside of the containers. So if you run the navnet container on your hardware, the navnet container itself can create the bridging interface or virtual Ethernet interface which connect to the inside the container and the outside of the containers automatically. And this is an example of the how the navnet container works. So the red line is a container border, and this is a one navnet base stations. So inside the container, there are many network interfaces appears, but this black line is a hardware border. So the host OS is running on the here. So if the navnet container has run, this kind of network interfaces inside the navnet automatically generated based on the configurations, and also the virtual Ethernet interfaces endpoint is created automatically to access the internal navnet container and host side. So if you want to connect this internal ENP1 devices inside of the containers to the real hardware NIC devices, you just bridge this endpoint to this network interface devices as a bridge devices. So you can control any kind of the navnet container itself and the real hardware or the logical other navnet container devices. So as you want from the host side. So this is a one test of the navnet operations. So we use three hardware. This is just like a bare-bone PC, which has 4 network interfaces. And you can buy this hardware for, I think, $300 or something. So very cheap hardware. And we operated the multiple navnet containers inside the one hardware. So for example, this hardware, we run 2 navnet containers and connected like this kind of string daisy chain networks. And are operated and connected daisy chains. And we evaluate some traffic, generate some traffic from this side to this side, and evaluate the throughput and round trip time. So this is a result of the throughput evaluation. So if we evaluate from this device VETH1 to VETH2, this is only connected internally. So the throughput is more than 4 gigabps. But if ETH1 to ETH3 here, so some gigabit Ethernet devices are passing through the passing through. So the throughput is the maximum throughput is 903.30 or 40 megabps. It's almost the peak throughput of the wired Ethernet throughput. And also we try to evaluate the performance of the 1 to 4 or 1 to 5 or 1 to 6. So the performance is keep remaining. So even if the container pass through, it doesn't affect the throughput. And also the round trip time. So the internal connection is a very short round trip time, also the 0.3 millisecond. But if the Ethernet cable pass through, it going up to the 1 millisecond. And if two Ethernet cable are pass through, it's going to the 2 millisecond. But it's a reasonable result. And that is a Ethernet network side technology. And we also developed some application service side service functionalities, which provides a node ID and a network locator resolver functions and DNS, DHCP, and also SIP server, SIP proxy functionalities, and the service ID and the terminal resolver and information sharing APIs. Such kind of functionalities we implemented and provided like as a Docker containers. And to using such functionalities, we need some application or framework applications to the mobile side. So we also developed some Android service platform framework applications to use the NavNet functionalities. So this is an overview of the framework, and the NavNet itself have a distributed database functions. And if you, the terminal side, want to use this kind of distributed database functions, you need to install these framework applications. And if the framework application is installed, the Android smartphone automatically register to the its CPURI and location information and IP address information to the base station, nearest base station automatically. And the base station also checking the link status and also the database synchronizing to the mobile terminal to the base stations. So from the application side, the usual Android provides Android OS provides some APIs to access the database. So from the application developer only use the Android OS APIs to access the database. So if some data is stored to the database, which maintained of the NavNet framework, the data automatically synchronized to the base station side. And also, if the base station database is updated, something, the data is pushed to the mobile phone terminals. And this operation is automatically operated. And using such database synchronizing applications, we demonstrate the voice message advertisement applications. So,
音声同歩です。
so this demonstration, the two Raspberry Pi, there are two Raspberry Pi, and the NavNet container is working on this Raspberry Pi, two Raspberry Pi. And there are 4 smartphones, and each smartphone are connected to each Raspberry Pi through the Wi-Fi interface. And if some voice are recorded, and that voice data is stored in the database in the smartphone, the data is automatically synchronized to the Raspberry Pi base stations. And then the Raspberry Pi, between the Raspberry Pi, also synchronize the database and push to the associated terminals. The data also push to the terminal side and also synchronize the data itself. And then the voice
音声同法です。
played among the terminals. So this kind of application we can develop using the NavNet API. And the key point is there are no internet connections and it's a private networks and there are no centralized server. And we just use the NavNet base station itself, container itself. So we can easily create such kind of applications using our frameworks. And this is real operations, which is constructed by the Shirahama town, Wakayama prefecture, Japan. So this is a very good sightseeing places, and there is a beautiful beach here. So many tourists comes to these cities, and to provide the Wi-Fi, public Wi-Fi access service. So Shirahama town creating this kind of NavNet networks for the backhaul network of the Wi-Fi, public Wi-Fi services. And when this characteristic of this network is there are two gateways for the wired internet access. And there are 3 points connected to through the satellite communications. So if one internet access line is disconnected, they keep communicating with this other through the other gateway. And if the both are disconnected, the satellite communication can be continue providing the internet access. And but the satellite line, the bandwidth is very limited. So if the many tourists want to communicate to the outside, it's a little bit difficult. It may have some difficulties to access the internet side, but they can keep communicating internally via the mobile phone application. And if some services on the NavNet itself, they can use the such local services, and even if the internet access is not available. So Shirahama town using this network for the emergency situations. The maximum is several megabps, but it depends on the plan, how many cost you pay for the monthly. So the minimum is 128 kilobps, and the cost is around 5,000 Japanese yen, so it's almost $60. Maximum. I need to check, but not 100 megabps. Yeah, several 10 megabps is the maximum. Yeah, this is an overview of the hardware side. So we just use the not special hardware, but commercially available. We combining the commercially available hardwares and create the networks. So the base station is it's like a PC, just PCs, and the Docker container, NavNet container is operating in these PCs. And this is another use case of the NavNet systems. And we collaborated with the ICT4D members to provide the network services in the rural area in Nepal. And we are testing now, start to install the NavNet system to the Duru area, which is located around here near the circuit. And almost 30 kilometers from the circuit. So we are trying to install, connect these areas using the optical fibers, which is a little bit special fibers. The fiber is also used for the Himalaya Everest communications, and provide using this fiber networks, and also some point a little bit difficult to connect using the fibers. So we use also the wireless fixed point-to-point links in some link. And the access side, we try to install some the NavNet functionalities and provide the local services like voice communications. Yeah, maybe the next speaker will introduce something about this project. And also, we are now trying to do some experiments in Sri Lanka. This is also the APT project, and this project we do some experiment to do some demonstration to create the smart village applications with the sensors and the emergency call, or several applications we are trying to implement using the NavNet platforms. We use Raspberry Pi for this infrastructures, and connecting some sensors to the Raspberry Pi, and also use the LoRa, private LoRa communication systems. So we also implemented some flattening protocol using the LoRa device. So if it can send the data and directly to the devices, and also they forward the data. So we support the multi-hop communications using the LoRa, private LoRa devices. So this is another experiment. And this is all of my presentation. And if do you have any questions? Okay, no problem. So let's move to the next speakers. So Abhimanyu-san.
HDMI.
Yes.
Okay.
Thank you. So my name is Abhimanyu. I work for a small nonprofit organization. It's a research organization. Our main focus is empowerment and development for mainly rural areas. So this is a lot of stuff which, and we'll share these slides, but basically it's something which can be done in rural areas, either across LDCs or development countries or even rural areas in any part of the world. I'll be covering basically what's going on in South Asia, the IoT landscape. And so let's get right on then. So basically going through certain definitions of what IoT really means. There's a pedantic definition, and then there's an actual practical definition of how it's implemented. And the various growth verticals in industry and personal use. Then I'll just cover a little bit of technology so people understand, just for the record, what IoT, what the different components are, the protocols, applications. And then there's a whole bunch of regulations which vary over South Asia. And I think we need to take a look at that. And finally, how does it affect GDP? Because money is the bottom line, and the time it takes, and how we can enhance research opportunities in South Asia. So there were two people who really came up with this IoT definition, and I think Peter T. Lewis is one of the founders, the father figures of IoT. Later, Kevin also gave a pretty compact definition of what IoT is, and it's basically, I studied control systems in undergraduate, and so these definitions are very fluid. So we'll figure that out as we go along. And so some things in the practical world, what IoT really is, what it needs, and what we expect from IoT. And, so there are sensors, and it's generally wireless. I mean, it can be wired, but generally. And when we speak of IoT, we expect these very small, low power devices you can spread out all over a landscape, collect data. It's not a communication network. It's just a small data network, sensor network. And I put one small use case here. So pharmaceutical companies need to send very temperature sensitive items across the world. So if something goes, if the temperature doesn't work across, the supply chain of maybe a couple of hours or days or months, how do we know that the product is good at the end of the 3 weeks of export? So are we able to collect exact temperature readings along its entire supply chain? So that's one of the use cases, and we'll go through more use cases later on. So so this is basically, and I've tried to put sources wherever I can. If I haven't, I apologize. I'll update it. So there mainly there are consumer verticals and industry verticals, and we have to be careful in the sense that which is which. Sometimes these blend, and the growth is going to be pretty spectacular. Now, I want you to remember this 6 smart objects per person number as we go along this presentation. The world population kind of is going steady, while smart objects are growing exponentially. So please keep this in mind. We'll come back to this important point. So, and now I just want to cover the protocols, how IoT is really implemented in the real world. So there are basically 2 types. One is the SIM-based, and one is the non-SIM based. So SIM basically means you actually have to get a SIM card or an eSIM card, and you insert it into every IoT device. So this is generally focused for towards telecom companies, because they are the ones who are generally allowed to provide SIMs. And there are many standards within that. Then there is a non-mobile network, non-SIM based IoT system. And these generally have LoRaWAN, Sigfox, and non-cellular IoT, Bluetooth, Wi-Fi. These are generally in the ISM bands. They allow for large-scale deployment. You don't have to insert a SIM in each end IoT device. And generally, this is more open source. I'll come back to the current industry, the NB-IoT versus LoRaWAN conflict at some point. So let's just cover a couple of things in the classical 4-stage IoT. So you have a sensor layer, which are these really small devices, usually they're wireless. They go to a network layer, which are gateways, which are aggregators pass through, and a data processing layer, which happens usually at the edge. So a little bit about edge processing right now. For example, the classical view was you collect data, you send it to the data center, you process it, take a decision, and send it back to the sensor. Currently, edge processing talks about making immediate decisions at the edge of the network. For example, especially in autonomous vehicles, you may not have the time or the network or the ability to make decisions at the data center and then send back the information. So you have to make immediate decisions at the edge of the network. And that's basically the definition of edge routing, a practical definition. There are multiple application verticals, and this is pretty much, across the world. I will focus more on Nepal's requirements and things which have really caused problems and which can be really solved at the societal level through IoT. So I just, this is almost the core of the presentation. In South Asia, India has taken a major lead in both NB-IoT, which is SIM, and non-SIM, which is LoRaWAN. Two examples, Tata Communications has deployed major gateways across India, and even states like Andhra Pradesh, they have almost gone into highly IoTized versions of smart water meters and so on and so forth. I've tried to put sources all across where I have received that information. Nepal, unfortunately, we're still at draft phase. What I heard last, they are still trying to regulate the LoRaWAN, the non-SIM based IoT. SIM-based IoT is allowed, and generally the players are NTC and NCell, but that's limited to TSPs. Bhutan amazingly has a very clear picture on IoT regulations. In fact, I talked to their regulatory authority. I sent them email. I wasn't expecting an answer, but the back and forth email went for quite some time, and it was really interesting. They were very proactive, and they gave me a lot of ideas and even documents which they hadn't placed on the internet. If anybody's interested, I can share that with you. Sri Lanka, their regulatory authority website is extremely nice, very clear, and they also allow both non-SIM and SIM based IoT. Bangladesh is a really great case. I want to point to 5B number 3. Right during the pandemic, Bangladesh's IoT DataSoft systems was able to create a software, IoT-based software for Hitachi. And they have got a lot of FDIs. They have got a lot of investment. So this really affects the GDP, which I will talk in some time. Maldives, unfortunately, I have not been able to get much information, but Tata has worked with some NB-IoT technology transfer there. Pakistan has also very clear regulations, and they're doing a number of projects, which is really good news for South Asia. So now, this is just a cut and paste, just to give you an idea what was happening in 2018. So percentage of national GDP was running, well, it was lower, in India, you can see it's pretty low. But this is 2018, and things are really going to change. And this is something which regulators across South Asia need to realize. as they make new policies. So now this again, I'm going to talk about scale and growth. Things are growing exponentially. Population is not growing exponentially. So the number of devices per person, as I said before, is going to increase. In our own homes, water meters, electricity meters, maybe other meters will be IoTized in the coming years, and we should be open and ready for that time, especially the regulators. So, this is a summary or the result of discussion with a lot of people in the industry. What does it need? What does IoT growth really need? And and this is a controversy. Many people feel that TSP should be controlling the IoT landscape. But as researchers, if you really want to promote growth, if you really want young engineers or engineers of any age to really adopt a new system, you have to use open systems. You cannot limit it to just the large players. The government needs to provide certain business incentives for startups, and through that, skilled manpower will develop automatically, which will actually help whether it's the large TSPs or the ISPs. And then you need to figure out, what does the end user really need? If you're going to give somebody who hardly gets water in the public tap, and you're going to install a 100-meter IoT device, that doesn't make sense. What does make sense is that if the person who's going to take the reading is being paid a certain amount of money per month, and if that can be a business case, if that can actually recover the cost of the IoT device, if that IoT device sensor can be cheap enough, work long enough, and not require constant maintenance, then at the society level, it will be accepted. And finally, so there are going to be multiple ecosystems of IoT devices and IoT systems, and the government needs to be ready to provide a platform that they can integrate with each other. For example, let's say you have water, electricity, and people talk about smart homes and smart cities. If you can get all this information together, have the right APIs, have the right data protocols, then it makes sense. If you have these verticals which are isolated and they don't talk to each other, then we might be causing more issues. This has been what is happening currently. It's a practical number of ecosystems. As you can see, LoRa and NB-IoT are the leading providers or the ecosystems, and the rest have kind of petered out. So we have to be ready for adopting both the leaders in the industry, and again, the authorities need to be ready for that. And this is a result of some discussion and debate with my friends in the industry. I give credit to Dr. Sebastian Butrick from Copenhagen University for providing this information. This is the source. So, and Dr. Sebastian is, unfortunately, he's unwell, but he'll be presenting online, I think. And so these are two major ecosystems, and we have to be ready for both of them. So way forward, the way we look at it is the policies have to be right. Ecosystem growth has to be encouraged. And finally, you need investment money, because you're not going to get a return right away. Break even might take a couple of months or years, depending on what kind of systems you're installing. The focus on Nepal, because I am from Nepal, is that we really need, currently there are draft regulations, and they talk about indoor and outdoor IoT, which since most IoT devices are wireless, that kind of becomes very controversial. So what is an indoor gateway versus an outdoor gateway if it's going to be wireless. What does indoor or outdoor actually signify? If I keep a gateway next to the window, is it indoor or outdoor? If I just put it outside the window, what does that mean? So these are questions which we need to really ask ourselves. Nepal is extremely complex. The geography is extremely complex. I have just come back from a tour from the Solukhumbu region. Things which look on Google Map are very different. And that makes it even more difficult to install IoT systems, whereas it also makes it more necessary to install IoT systems. Power requirements have to be extremely low in Nepal. There are places where you can't even charge a mobile phone. And the reach has to be extremely high because even small ward areas can take maybe a week or 2 weeks to travel through, especially the Khumbu region, for example. Immediate needs, which I discussed with my friends and people across the industry, are perhaps tourism and agriculture, and there's one more, we'll come to that. So focus on Nepal. This is like what really needs immediate focus. And I've provided sources for this, and traffic accidents. It's something which is very, perhaps cannot be fixed by IoT, but there are many accidents which we don't even know where it happened and how to reach those places. Many accidents happen in places where there's no mobile network. I was coming back, and last night, actually day before last night, I saw a burnt Tata Sumo car on the road. And the driver in my car, he told us, he asked us, you know what happened? And I said, no, but it was completely burnt. He said, well, somehow the car overheated and it burned. And I said, what happened to the people? All the people were saved. They were able to save their items. Unfortunately, there was no mobile network. So they had to walk for maybe 3 or 4 hours just to be able to inform the police that this is what happened and blah, 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 and to get some kind of support. So, and this is a use case which is not unique across Nepal. It happens in many places, especially in the upper regions. Tourist tracking. This is a very serious issue. I think if tourism is going to be made the backbone or one of the strong pillars of Nepal's economy, then we have to make sure that we can actually find the tourists if they go missing. And it does happen. Again, I was in the Everest region a couple of days ago. Stories from the ground, 9 tourists have already gone missing. They were able to find bodies of 3. Families come over, they're desperate. We're not able to track them. And this is something, again, which is a major use case which IoT can provide. There's something which I just was informed recently during my trip: livestock insurance and tracking. In the upper hills and mountain areas, yaks move around from region to region. Climate change during change of seasons. Sometimes they go for grazing grass. Sometimes they get thrown off or they fall off the cliff, although they're very sure-footed, but it does happen sometimes. And to track them, actually, for insurance purposes, they have a small tag on their ears. Now, these are not RFID tags, these are just normal tags. But if you can just, but what it does prove is that these animals are accept certain tags. And if we can install GPS trackers or some kind of RFID tracking, it would be acceptable. I have a small clip I'll show you in a short while. And so this I was walking and I took this clip. Let's see if I can find the exact. So as you can see, there is a yellow tag on the ear of this mule. And yaks also have this similar tags, and many times animals go missing, and this is something which I think would really assist local. Mostly these are poor farmers, lower middle class farmers, and it would be a use case which would certainly help them. So that's about it from my side, a bit of what's happening in South Asia. If you have any questions, please, or any suggestions. Yes, sir. Thank you, sir.
Now, what type of study is going on in South Asia in healthcare systems? Yes, sir. Can you please elaborate healthcare?
IoT in healthcare? Oh, sure. In South Asia. I'll give you a global perspective and then I'll talk about South Asia. So personal health monitors, especially like non-invasive sugar meters, oximeters. In fact, it's a great question. I was coming back from Gorakhpur, which is in about 5,200 meters. I was coming back. And behind me was a Sherpa guide, so a local person. His oxygen level had fallen to about 65 and he was rushing back. And I was surprised. I said, you guys are local. Your oxygen levels are generally better than the rest of us. And he said, it's nothing like that. I said, how did you test it? And he said, I had an oximeter, but all along the way, I was, checking myself, every half an hour or something. And then it got me thinking, let's say if we had an IoT-based oximeter device, which you can just attach to your skin, non-invasive. And if you put this, especially after 4,000 meters, when things start getting serious, and you kind of mandate all tourists, or you actually get some kind of, that if you don't put it, then we won't be responsible kind of term with them. At least you can check their sugar levels, their oxygen levels, as they are traveling through these upper Himalayan regions. I met a woman who was actually on a horse, and she was going towards Gorakhpur. She was actually climbing, and her oxygen levels were 45, which is extremely dangerous. 60 is about the limit. Anything less than 60 in those regions, you have to come down. And she had pressured her guide to take her, because she had paid the money and she still wanted to go. And we kept telling her, go back, go back. You can come back another day. So I think these things need to be, because if tourism is going to be considered one of our major pillars of the economy, then we have to make sure that, yes, people get a good time, they get a nice adventure, but they also come back safe. Nobody wants to die. I mean, everybody wants an adventure. So I think if that answers your question to some extent. Thank you. Anything more? Any suggestions? Any ideas? I think those in Nepal, and I think anywhere across the world, I think if you focus on what's the most important societal requirement, I think you will find a use case to regulate IoT policies and ensure that research institutions, small, smart startups, as well as the big TSPs, they get into the space. But I really think that unless you bring in researchers and small startups, you will not be able to grow this system to a large extent. I think when we look at Bangladesh and Sri Lanka and India, of course, they're really leading South Asian IoT deployments, and then in Nepal we can learn from them. Yes, sir.
So, there be I'm from Nepal. Should there be some kind of rebate in internet uses for systems to be implemented? internet is costly when we are going to implement IoT in terms of internet uses?
So the basic IoT, let's go back to so as you can see from point number 6, IoT is not a communication network. It's not, you're not doing, large scale communication. You're not sending large images. It's mainly about saying yes or no. There is a problem. Oximeter levels are 65, 45, 95, very small data packets. We're not so, even when you scale it up, yes, there might be an issue, but for that individual user itself, the cost is not going to be that much. We're talking kilobytes, not megabytes. Yes, when you have 50,000 tourists across the Himalayan region, everybody sending a couple of kilobytes, it does add up to the network. And there have been discussions on having a separate IoT data plane, which does not interfere with the mobile network or the mobile communication network or the mobile data network. But to the individual user, it's not going to be a major cost. If I answered your question. Yes. I can share the regulations from Bhutan Regulatory Authority, and they have done some very extensive research and a very nice concept paper on how they are going to separate the IoT data plane and the existing mobile data plane. So they have done some really good work. I couldn't find much information on actual deployments, but the government is very proactive. Their authorities are very responsive. And I think we should take a look at countries around us, Bhutan, Bangladesh, Sri Lanka, India, Pakistan, and how they are doing work there. And they have done some excellent work, excellent work. Yes, sir.
Thank you very much for your very comprehensive work. And do you have any suggestions for telecom operators in Nepal? Actually, we are from Nepal Telecom. And from your presentation, I understand that we are way back from other countries in the South Asian region. Do you have any idea or suggestions about this new Karyavidi from NTA on IoT? Were you involved as well or something like that? Thank you very much.
Thank you for your kind words. No, I wasn't involved directly, but since we are having an open discussion, Dr. Sebastian Butrick from Copenhagen University, he came in 2019 for personal tourism, and then at the same time, I think he knew many members of our nonprofit organization. He knew Dr. Bhushan from before. He knew Pawan Sakya from before, and he really introduced me to IoT, the Things Network, and so on and so forth. Truth and disclosure, I am biased towards more the research side and more towards the non-SIM side of IoT, but I understand the necessity for having large TSPs to boost IoT deployment. I understand that because they have the money, right? But we must not forget the researchers. We have, our organization has a MOU with KU and Prime College and other institutions in which we are trying to promote IoT. And I spoke to Mr. Amber Stapit from NTA, and he really forwarded, or he really encouraged us. And the LoRaWAN frequency, 865, 867 megahertz, that actually is currently stuck in the frequency committee. Now, getting information about what happened or getting the meeting minutes from such a committee are quite a challenge, but this is the inside story. I do wish that NTC would also encourage and invest in researchers. This is how it works from my experience across the world. that when you encourage these small startups and researchers, eventually they come back to help your own company. So tomorrow when NTC is going to hire 50 IoT engineers, maybe they might come from the LoRaWAN community and they will start working in NB-IoT. So it will be help for NTC as well. Not only that, there are certain regulations in the NTA draft framework which need a little bit of revision, like indoor versus outdoor. What is indoor? What is outdoor? What is, where is that division? And in wireless, does that even make sense? And so I think agencies or institutions like NTC, I think they can really benefit from LoRaWAN or Sigfox or non-SIM-based IoT. It will eventually help them. Our investment in our communities and our research institutions eventually comes back to help us. For example, IBM bought Red Hat Linux. So Linux is open source, right? And IBM is as proprietary as you can get in this world. But they did buy it and they're getting help from that. So this is a back and forth. I'm not going to say NB-IoT is incorrect. I just think that if you work together, more can be done in Nepal. Because at the end of the day, even gateways, if we can use shared infrastructure, if you can use the same telecom towers and use the same telecom backbone, then why not? Then why not? Deployment can be faster. NTC can have a stake in that. I mean, after all, it's a public company. It's got share value. So I think working together, collaboration, I think that's the age of this, the mantra of this era, and we have to work together. Thank you, sir. Thank you.
Okay. Just
for startups, this IoT use cases in the Southeast Asia, if you have anything to share.
Well, I know that ICT4D ourselves, we want to do a lot of work in water meters in LoRaWAN, and I myself did a lot of research, and Dr. Bhushan has done a lot of research in waste management, because what happens is these trucks which collect the cess from your septic tank, they're supposed to dump it in a very specific place. Many of them in the night, they just dump it in the river, So with IoT tracking, you know exactly what that truck driver is doing. Is he going to the waste processing plant, or is he going somewhere else? And that affects the health. I mean, so a small investment in IoT can make a big difference to our river water health. And I think anybody from Nepal knows the health of our rivers. This is land of rivers. Unfortunately, we haven't respected it. So, yes, sir.
Okay. Sorry, the time is very fishing. So this short one, please.
Like in Thailand, I'm Rauluk and I'm working in Thailand. And in Thailand, we have deployed our own LoRaWAN gateway and we have our own Things Network private server. But now we are facing the challenge of duty cycle. Like we can send at most 100 messages per day from one device. So for tracking, we need much more than that. So how do we overcome the challenge of duty cycle of LoRaWAN?
I might not be able to answer the most technical details on LoRaWAN. I'm certainly not an expert, but generally what I have seen is that duty cycles cause problems based on the quality of your gateway. I know, and I'm certainly not an investor or a promoter of Kerlink, but I worked with Kerlink a lot in the hope that they would come into Nepal. Tata has invested heavily in Kerlink gateways. It's a European company. And they proclaim that they can connect to thousands and thousands of IoT devices. I don't have the exact data, and I apologize for that. But if you need, we can have an offline discussion on this, and definitely we can work together. Thank you.